So let's start with the first one. So what mass of oxygen was reacted with the aluminum? So if you read the problem, it says that suppose a sheet of aluminum gains 0.09 grams. So if you had aluminum and it gained 0.09 grams, that means this must be oxygen, right? So it's actually, oops, I don't know where it went. That 0.09 grams, that's the actual amount of oxygen that was reacted. So now the next question says, what's the mass of aluminum reacted? So if we have 0.09 grams of this, all we need to do is convert this to aluminum. Now this first step, so we're going to go from grams of aluminum to moles of aluminum, and from moles we're going to go to grams. Okay, so when we do this, 0.09, and I'll worry about sig figs at the end, but we will talk about sig figs because that is on your exam. So we have grams of oxygen. This first step, this is something that you will see on your exam, right? There's 32 grams of oxygen in 1 mole of oxygen, right? So if we were only going to moles of oxygen and we got our answer, that's something you're going to see on this exam, right? Going just from grams to moles. But in this case, we want to go to grams of aluminum. So whenever we have something, but we want something else, we have to do a mole-mole ratio. And remember, these mole ratios come from using these balanced chemical equation. So there's 3 moles of O2 to 4 moles of aluminum. Oh, great question. Why 32 grams? This is O2. So we have to have 16 times 2. And that's why we have 32 grams. Okay, perfect. And now, in this case, we want mass of aluminum. So if we stopped right here, we would end up with moles of aluminum. But the question asked for mass of aluminum, hence why these units are so important. And in 1 mole of aluminum, I don't have my periodic table, but I think aluminum's 26.98 grams. Can anybody verify that?
Yes.
Okay, perfect. Okay, so now I want everyone to put this in their calculator to see what they get, because again, calculators are going to become very important this weekend for your exam. Okay, so let's see what everyone gets. And to review for your exam, make sure your significant figures are correct. So everyone put this in your calculator, pretend this is like something you would have to do for your exam, and then check your significant figures. And then type your answer in the chat. And again, you can always type it privately if you don't want it to show up publicly. That's always okay. So I'm going to wait for a few of these.
Professor, can we still come to lab for like any homework questions?
Yeah, absolutely. If you have any homework questions, feel free to come in during the Zoom sessions and ask. Yeah, that's totally fine. So either 3:30 today or 3:30 Thursday, and then I'll be there during the Zoom sessions until everybody leaves. I usually stay.
Do we have to show up for at least 1 Zoom session?
You don't have to, no, but I suggest you do. Again, this week's lab uses this, which gets really, really, really hot. I'm going to say this like 10 times. Make sure you don't touch it with your hands. Make sure you don't put it on paper or plastic or wood, or I mean like your wood table, because you'll wreck it. Put it on a hot plate. Okay. I'm seeing lots and lots of answers. Okay, so let's first look at sig figs. As a review, how many sig figs is that? Yeah, 3 sig figs, right? So this is 3 sig figs. So our answer needs to have 3 sig figs. 101 grams of aluminum. Now, if we put this into, so just to review our sig figs again really quick here, right? Decimal places present, start from the Pacific, doesn't count, doesn't count. 1, 2, 3 sig figs. Again, start here, it doesn't count. 1, 2, 3 sig figs. If we put this into scientific notation, right, our answer in scientific notation would be, we move our decimal place one place, 1.01 times 10 to the -1 grams of aluminum. So make sure you're good with going from scientific notation and back and vice versa. Okay, so that is our first one. I'm going to show it to you neater now. There it is, so much prettier. And again, this is not new and this is not new. This is the stuff that's on your exam. The only new piece is this. That's the only new piece. So pretty much we're doing exactly what we're going to be doing for your exam. Okay, the next question was how much aluminum oxide is formed? Okay, try this one all on your own, and then we're gonna go through it together. And again, when you put your answer, type it in the chat and make sure you consider significant figures with your answer, right? I don't know the molar mass of aluminum oxide, by the way, but that's a great question. Like on this exam, one of the questions is going to be like, what is the molar mass of aluminum oxide or Al2O3? So I'm not even going to tell you because those kind of questions are going to be on your exam. So try all this question right here, type your answer in the chat, and then we're going to go over it in just a minute. Okay, didn't mean to show you the answer there. I'm seeing a few come through. So keep going on this. Again, make sure you add that molar mass because that's great practice for your exam. This whole problem is great practice for your exam. So I'll give you another minute because I want to make sure everyone puts this in their calculator to make sure that we can get the right answer also. Okay, seeing a lot of them now. So when we start with this, I'm just going to start with our oxygen. So 0.09 grams of oxygen. And again, we need to get to moles because we want Al2O3, but all we have is oxygen. So if we want to convert from one to the other, we have to use a mole-mole ratio using these coefficients. So we have to get to moles. And again, this is 32 grams because it's O2 in 1 mole of O2. Here's where the mole-mole ratio comes in, 3 here. We want to go to Al2O3. And here's our molar mass, 1 mole Al2O3. And the molar mass is, I got 101.96 grams of Al2O3. And I'm seeing lots of correct significant figures. 0.191 grams of Al2O3. Remember, whenever you look at the periodic table, so this number here we got from looking at the periodic table. The number above or below it is always 1 mole. Because remember, the units of the periodic table are grams per 1 mole. It's the number of grams in 1 mole. So if you ever look at the number from the periodic table, below it or above, 1 mole, right? From the periodic table, below it or above it, 1 mole. The only time you're going to have a number that is different than 1 mole is when you have a mole-mole ratio. So let me just erase this so you can see it prettier. I have it prettier right here. This is the only time you ever have a number that is different than 1 mole, right? And these numbers come straight from our balanced chemical equation, right? Otherwise, it's always 1 mole, right? If you ever look at that periodic table, you had to look at the periodic table to get that number. On the other side, it's always going to be 1 mole. And this, by the way, should be Al2O3 here. I'm not sure how I missed that, but okay. All right, so we're good on this. Any questions? All good? Okay, so now we're gonna take this one more little step here, and this is gonna be limiting reactants. And so when we're doing limiting reactants, when we mix 2 reactants together, they're not both used equally. One of them always runs out first, right? And the other one, we just have more of it. But we can only make as much product as we have limiting reactant. So in this case, we actually did this. We put metal, we put magnesium and hydrochloric acid a few labs ago, and we watched it like all disappear. Remember our gas one, when we like made gases, right? If you can see here, so here's us putting the metal in the acid. In this case, so this is, I'm gonna just, hold on a second, let me just write this one. This one is A goes to B, and this one is A goes to B. They're the same reaction. Actually, you know what? I'll just write the whole reaction right here. So we have magnesium plus HCl goes to H2 gas plus. Remember this? Oh, we all loved that chapter, right? We loved it. So in each of these cases, these are our reactants. So here is, I ran the reaction 2 times. When it's over, right, we have these products, but you can see, look at, there's extra magnesium sitting on the bottom here. We have magnesium left over. So magnesium is what we call our excess reactant, and hydrochloric acid is our limiting reactant because we ran out of hydrochloric acid. We need more hydrochloric acid in order to dissolve this magnesium, and we don't have enough. So hydrochloric acid is our limiting reactant, and magnesium is our excess. See how I write it excess? Because look, we've got extra of it. Now, The next case, so here I ran that exact same experiment again, exact same experiment. But in this case, look, there's no magnesium left at the bottom. So that means that we must have excess hydrochloric acid, and magnesium was our limiting reactant, because look, there's none left. Well, now we're going to learn how to do that with math. But before we do that, we're going to do it with food. So again, what is the limiting reactant? So the limiting reactant is the reactant that reacts completely, and so there's none of it left in the end. And so its amount determines the amount of product that can form. So let's do this again with cheese sandwiches. Again, cheese sandwiches. Okay, if you have 20 slices of bread, remember, basic cheese sandwich, 2 bread, 1 cheese, that's it, no extra cheese. So if we have 20 slices of bread and 8 slices of cheese, how many sandwiches can we make? Yeah, I'm seeing tons of them. 8, because we only have 8 slices of cheese, right? We only get 8 sandwiches, right? Now, if we look at this, how many slices of cheese would we need if we were going to use all 20 slices of bread? We would need 10. Yeah, very good. But we don't have 10, right? We don't have enough cheese. We only have 8 slices of cheese. So therefore, cheese is our limiting reactant. Okay, so, and we all just did that in our head, right? All we're going to do is now we're just going to apply that to chemistry in a little bit, but it's the exact same thought process. You have 2 reactants. One of them you're going to run out of first, right? We ran out of cheese slices at 8, right? At 8 cheese slices, when we got to 8 cheese slices, we ran out, right? So therefore, we could only make 8 sandwiches. We'll do a little math with this in a second. We can only make 8 sandwiches. And then we've got a bunch of bread left over. So cheese is our limiting reactant. It determines, the limiting reactant determines how much product we can make. If we only have 8 cheese slices, that means we can only make 8 sandwiches. So your limiting reactant determines how much product you can make. So let's just do this one with a little bit of math. So the limiting reactant is the reactant that you run out of first, right? It determines how much product can be made and how much of the other reactant will be used. So what we're going to be trying to do is we're going to try and identify who the limiting reactant is, and then how much product can we make. Okay, so once you identify your limiting reactant, by the way, you always start the calculations with the limiting reactant. So if we have 8 cheese slices, we look at the relationship again between cheese, right? Cheese and sandwiches, and we have 8 sandwiches. And again, that's exactly what we did in our head. Okay, so I want to try, actually, we'll just keep going. And again, however you like to write this. Okay, so now let's do this with chemicals. So if you have a bunch of people CO2 molecules, right? And we have a big old jar of carbon and a big old jar of oxygen. And we have our balanced chemical equation above. If we do this, we look at how many carbon atoms we have. So we count 1, 2, 3, 4, 5, 6, 7, 8, right? We have 8 carbon atoms. How many oxygen molecules? So if we have 8 carbon atoms, how many oxygen molecules do we need to react with all of the carbon atoms? We would need 8, right? Because 1 carbon plus 1 O2 makes 1 CO2. So therefore, if we have 8 carbons, we would need 8 oxygens to make 8 CO2s. But we only have 1, 2, 3, 4, 5 oxygens. So we're going to run out of oxygen before we're going to run out of carbon. So if we react these, we can only make 1, 2, 3, 4, 5. Because now we have no more oxygen, right? We can only make 5 CO2 molecules. We could never make 8 CO2 molecules, right? There's no way we could have ever made 8 because we don't have any oxygens left. We just have these 3 carbons sitting around just doing nothing. We could have never made 8. The maximum we could make was 5 because we only had 5 oxygens. Okay, so now let's try this again with moles. Okay, so if we do this, first, same questions, just with moles. I'm going to show you like the little bit of a math of it. If you have 8 moles of carbon and 5 moles of oxygen, how many moles of CO2 can be produced? So what we're going to do is I'm going to start with, first, my 8 moles of carbon. And I'm going to convert this. Actually, I'm going to do this a little bit different. So I'm going to convert both of these to CO2. So if I have, I'm going to write it like this. So I have carbon and I have oxygen, right? And I have 8 moles of carbon and I have 5 moles of oxygen. Now I'm going to see how much CO2 I can make. There's 1 mole of carbon for every 1 mole of CO2. That means 8 moles of CO2. Do the same thing here. I'm going to convert this to CO2. 1 mole of O2. Again, I'm getting that right here. 1 mole of CO2. I'm going to do this. 5 moles of CO2. Now, only one of these processes, only one of these, either the top or the bottom, is real. The other one doesn't even exist. The reason is because we ran out of our limiting reactant. If you look at this one says we can make 5 moles of CO2. So when we use all 5 moles of oxygen, we can make 5 moles of CO2. When we use all the moles of carbon, we can make 8 moles of CO2. But we ran out of oxygen after 5, because after we used 5 moles of oxygen, we had no oxygen left. So we could have never made 8 moles of CO2 because we only got to 5. Once we got to 5, we had no more oxygen left. So this is like an imaginary thing. It never actually existed. So here's how much product we can make, and oxygen is our limiting reactant. Okay, so now I'm going to show you that with a little bit more, ignore this here. So it's kind of what we just did before. 5 moles of CO2. Okay, so now we're going to do it with numbers we haven't seen before. Okay, now when we're doing limiting reactants, there's a couple different ways to do this. If you've learned it a different way and you like it a different way, totally fine. If you have another way that's to do this and you like your other way, totally fine. I'm just going to show you what I think is the easiest way to do it, the most direct, a little bit more math involved, but a little less thought, which helps us get it right. So what we're going to do is we're going to take both of our reactants and we're going to convert them to products. Here's our product, MgO. And we want moles of MgO. So we have we'll start with 12.5. 12.5 moles of Mg and 7.3 moles of O2. Oh gosh, sorry. We want moles of MgO. Okay, so now a lot of times people are like, how do I know if I need to do a limiting reactant? Because they give you two numbers, both reactants. They gave us Mg and they gave us O. We have to find out which one is gone first. So what we do is we start with both of those. So we have 12.5 moles of Mg, and then we have 7.3 moles of O2. We're going to convert both of those to MgO. Whichever one is smaller, that's going to be our limiting reactant. So moles of Mg has to go on the bottom, and I'm going to have this 2 moles of Mg. And I'm going to convert this to our product, which is MgO. When we do that, we get 12.5 moles of MgO. Do the same thing again. There's a 1 here. 1 mole of O2. So we're just doing the same thing twice. That's basically what we're doing. Nothing new. We're just doing it twice. 2 moles of MgO. Again, that 2 came right from here. And we do this, we get 14.3. No, 14.6. I can multiply. Okay, now only one of those is real. The other one, not real. How do I know which one is the actual answer? Okay. So by the way, this is the same thing we've done before, right? So we've done this before. This new part, trying to figure out which one of these is our answer. Only one of these is our answer. The other one never actually occurred. It's imaginary, right? The smaller number, exactly. The smaller number is your answer. So this is your answer. So in short, the smaller number is always your answer. The reason is because when we used 12.5 moles of magnesium, we made 12.5 moles of MgO, and then we had no more magnesium. It was gone. So at 12.5 moles, we had no more magnesium. Reaction stops because we don't have any more. Now, when we did the same thing with oxygen, it said we could make 14.6 moles, but that's imaginary because we ran out of magnesium at this point. So this one down here, this never even happened, right? So when we do this, you end up with one that you're going to use and the other one you're just not going to use. You're going to look at the smaller one. That's going to be your answer. So this is the amount of our product that's produced. Our limiting reactant is what you start with. When identifying your limiting reactant, it has to be a reactant. You have two choices. Your choice is either magnesium or your choice is oxygen, because those are the reactants. A lot of times people will say, oh, this is my limiting reactant. No, magnesium oxide is a product. It cannot be a limiting reactant because it's not a reactant, right? So when you identify this limiting reactant, it has to be a reactant. Okay, so now I'm just going to leave those. So here's kind of where we ended up. 12.5 moles of MgO, right? Same thing, just neater. Okay, now let's use that exact problem that we did last week. Remember this problem that we've now done like a lot? So in this case, I gave you the balanced chemical equation. It says how many grams of oxygen can be produced when 14.7 grams of KO2 is reacted with 27.5 grams of CO2. So now the question is, how do you know it's a limiting reactant problem? Well, 14.7 grams of KO2, they're giving us KO2. They're saying we have 14.7 grams of this, 27.5 grams of this. They're giving us two reactants, and they want grams of that. How do you know if it's a limiting reactant problem? They give you masses of two reactants. You have to find out which one gets used up first, right? Whichever one gets used up first, that's going to be your answer, right? That's going to bring you to your answer. So now, when you set these up again, you're going to have two problems. By the way, if you can do this faster than me, go ahead, do this faster than me, and just type your answer in your chat. So we're going to have KO2, and then we have CO2. We're going to convert both of these to grams of oxygen. Whichever one ends up being the smallest, that's our answer. So now we'll do the KO2 first. KO2's molar mass, by the way, was 71.1, I'm pretty sure. And again, that was just from adding it up on the periodic table. Good practice for your exam. Okay, now what I'm going to do here is I'm taking KO2, I'm converting it to O2. I had to go to moles because the only way I can convert from KO2 to O2 is to get to moles. Well, I'm at moles now. This is when we use those coefficients. The 4 has to go on the bottom because this unit's up here, so I have to put it on the bottom. I'm trying to get to grams of oxygen, so I'm going to go to moles of oxygen. This is by itself, so it's a Brinkelhoff, so we need to remember in 1 mole of oxygen, it's 32 grams of oxygen because it's O2. And that gives us something. I don't know what that gives us. And then the second one, actually, I think I'm going to have you set up the second one because it's really good practice for your exam. So set up the second one and then tell me what you get. And I want you to think about significant figures too. Oops, while we're doing this. Okay, so set up the second one. Tell me what you get. You can type it in the chat and then we're going to figure out which one's our answer in just a minute. So try that and then we'll do the rest of it together. So I want you to try this one. We're going to convert from CO2 to grams of O2. Great practice for your exam. Okay, so I'm seeing a bunch of them come through. So I'm going to finish this. Again, this first step, great practice for your exam. I'm sure CO2 is 44.01 grams, right? I think so. Is that the right molar mass? Just going off my memory. Okay, good. 1 mole of CO2. Again, this is exactly what you'll be doing here. This is your exam, right? The one this week, you'll be doing things like that. This is our only new step we have right here. So we have 2 moles of CO2. And again, we're going to oxygen, and there's a 3 in front of the oxygen. But we're going to go to grams because they asked for grams. 1 mole of O2, 32 grams of oxygen. And let's see here. So we're going to do this. This one we ended up with, this one is what, 4.96 grams of oxygen. And this one I got, 29.9 grams of oxygen. So you see here we have 2 answers, right? And I saw some had like 30.0, that's fine. It depends. Little small differences, like if you have 29.9 or 30.0, or if you ended up with 4.97 or very close, because of the molar masses, sometimes you get tiny bit difference of an answer, but as long as it's close, it's okay when we're doing these. Okay, now, only one of these is real. The other one, not real. It's an imaginary problem that never existed. So which one of these is correct? The 4.96 or the 29.9? Which one of those is real? Like which one actually occurred?
The smaller one.
Yeah, the smaller one. This one is our actual answer. This never happened. It's imaginary. Yes, we did a whole extra bit of work there, but what does this mean? So when we used 14.7 grams of KO2, we made 4.96 grams of oxygen, right? After we made this 4.96 grams of oxygen, we had no more KO2 left. It was all gone. So after we made 4.96 grams, there was no more KO2. Bye-bye KO2. Without the KO2, the reaction can't happen anymore. It stopped. At 4.96, it was over. So this answer down here said 29.9, but that's imaginary because we could have never gotten there because after 4.96, the reaction stopped because we had no more KO2. So this is our answer. Our limiting reactant, again, has to be a reactant, is the one we started with, right? And it's the one that you ran out of first. So as you can see, these limiting reactant problems, you do these, oh my gosh, all the time in Chem 219, like all the time. But it really is exactly, it's just building on what we learned from the mole, and then we just learned how to do these mole-mole ratios, and you just do the same problem twice. Pick the smallest number, whatever you started with, that's your limiting reactant. And that's limiting reactant. It's just like one more tiny baby step. Okay, so when we're doing this, we always have to go from grams to moles. The key to limiting reactant is the only way you can go from one to the other is moles, right? So you always have to convert to moles, right? So, okay, so now let's try one more problem. This one's kind of a long one. Okay, how many grams of AGBR can be produced from 50 grams of MGBR2 and 100 grams of AgNO3, and how much excess reactant remains? Okay, so let's look at what do we have. So we have 50 grams of this, and we have 100 grams of this. And it wants grams of AGBR, so we want grams of that. Okay, so first of all, how do we know it's a limiting reactant problem? Well, they give us grams of this reactant and grams of this reactant. We have to find out which one gets used up first, right? So this must be a limiting reactant problem. Okay, so on these limiting reactant problems, what we do is we have two problems. We convert this to our product, and we convert this to our product. So it's two separate problems. Now, again, the reason we're going to AGBR is because it asked how many grams of AGBR. So we're going to convert both of those to AGBR. Whichever one is smaller, that is our limiting reactant. Okay, so I'm going to give you a couple minutes because I want you to try this one all on your own. You have a nice, beautiful, balanced chemical equation, right? So you have your moles. You just need to add the molar masses, which again, those molar masses are going to be all over your exam. So that's a great piece. So I want you to try this and then tell me, I want to know how many grams of AGBR and who is the limiting reactant. And then this second piece, I'm going to show you how to do that. We'll do that piece together. But try this first piece together. So 1, how many grams can we make? 2, who's the limiting reactant? Okay, try this. Great practice. And then we're going to go over this in just a minute. And if you're watching this later, try this problem. Again, this is literally what we do the entire rest of the semester almost. And 80% of Chem 219. So this is a really important concept. And once you get it, chemistry is a much happier subject. Okay, try this and then we'll go over it in a few minutes. And if you have any questions, just ask. You can either text me, say it out loud, or type it in the chat. Either of those will work. All right, so I'm seeing a few of them come through. So let's start with the 50 grams of MGBR. Again, I'll worry about my sig figs later. So the molar mass, your molar mass should have been about 184-ish if you added it up from the periodic table. In 1 mole of MgBr2. Okay, so now that we're at moles, now we can use our balanced chemical equation and convert from MgBr2. So 1 mole of MgBr2 to 2 moles of AgBr. And then again, we're going to go to grams. 1 mole of AgBr. And the molar mass is about 187.4-ish grams of AgBr. So I got about and around 102 grams of AgBr. Now if we look at our sig figs, 3 sig figs, 4 sig figs, our answers are all going to have 3 sig figs, right? It's going to be the least amount. Okay, so that's the first piece we did. Cross, 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 cross. Grams of AgBr. Okay, so now that's our first one. Oh wait, no, look, I had it right there, perfect. Right, so there's our first one we did. And then we have our second one. So I'll just do it under this because it's right here. So 100 grams, and again, of AgNO3. So again, some people like to just stop at moles and then go to the next step. That's fine. There's so many different ways you can do limiting reactants. There's at least 3 ways that I could show you right now. This way just seems to be people's favorite, and this one seems to be the one people like the most. But if you have another way, if you learned a different way, you can absolutely do that. So this first step's exactly the same. Actually, it's not exactly the same. I was just recopying that. Sorry. It is 169. Thank you. 169. The last step is exactly the same. Grams of AgNO3. 1 mole AgNO3. And again, the reason I'm doing this first step here, so it's the same thing, I'm going to convert to moles so I can get to this mole-mole ratio. So I'm converting to moles here so I can get to this mole-mole ratio. And again, when this mole-mole ratio in this case, it's 2 to 2. So 2 moles of AgNO3 to 2 moles of, and again, we're going to AgBr. So we're kind of doing the same thing. We're just doing the same thing. We're just changing what we're talking about. We're talking about AgNO3. And now this step is literally the exact same. So I'm going to go to grams. And again, if you have a different way that you want to do it, that's fine. And I got 110 grams of AgBr. Sorry, it's a little messy. I'll make it nice. Okay, so let's see here. All right. Oh. Okay, so when we do this, just checking out some of these. So I'm going to put this in my calculator, make sure I calculated these right. So let's put them in our calculator so you to make sure that I calculated these right when I did this. 169.9 times 2. Yep, I got 110 for the first one, the second one. And I got 102 for the first one. Okay, so I just redid these calculations, 102 and 110, both of those are correct. So make sure that you're getting both of these in your calculator. If you're doing this now, or if you're doing this later, make sure you're getting these in your calculator. These are great practice problems for using your calculators. Okay, now only one of these answers is real. The other one's not real. If you got 111, yeah, you might have gotten 111 just because I only went one place past on my molar mass. So as long as you got about, like if you got 101 or 103, you're okay, or 110, 111, that's okay. As long as you're about and around on these. And again, it totally just depends on your molar masses. On here, usually I always go 2 places past, like on the molar mass, like if it was like nitrogen, is 14.01, but in this case, I only went 1 pass, so my molar masses are probably slightly different than yours. So that's okay. Okay. All right, so which one of these is real? Only one of these is real. The other one is not real. So our choice is either 102 or 110. Which one's real? And which one's like, nope, never happened. It's imaginary. I'm seeing a few. Yeah, the smallest one. This one is real. Here, I'm just gonna put this. I'm gonna make it, hold on. I have it neater with them all together. This is much prettier now. Okay, so I flipped them, sorry. Here's the second one. This was the first one. This one is real, the 102, right? The 102 is real. Yeah, it's always going to be the smallest number. The smallest number, that's your answer. This never happened. All that work, we can't use any of it, and we can never use it. Once you find this smaller number, you don't need to like black it out, but you're never using it again, ever. There's no reason and there's no possible way you're ever going to use it. So just ignore it from then on. Your limiting reactant, again, has to be a reactant. It's the one you started with. That means that we used up out when we used 50 grams of MgBr2, 50 grams of this made 102 grams of this. After we used our 50 grams, we didn't have any left. So the maximum we could make was 102 grams. We could have never gotten to this 110 because after 102, we didn't have any of this left. It's all gone. We just had this sitting around, right? So we couldn't make any more product because it was gone. So that is how we find our limiting reactant. Again, it's always going to be the one you start with. Your product, the amount of product is your answer. You get the smallest one, always the smallest one. Now, the next step is how much excess reactant remains, how much extra is left. Okay, so now this piece, it's one more tiny piece here. Okay, so after we made 102 grams of AgBr, right, we had some of this left over. This is our excess reactant. This is our limiting reactant. We want to know how much was just sitting there. Like after we used all of this up, how much of this was left? Okay, so we started with 100 grams of this, but we didn't use all 100. We want to know how much of it did we use, right? So how much of it did we use? Okay, so we want to figure out how much we used. We know that we're going to use all 50 grams of this. So if we use all 50 grams of this, I'm wondering how much AgNO3 is used in that process. So to figure out how much excess reactant you have left, all you do is you take your limiting reactant and you convert it to here. So what we're doing is we're going to react the 50 grams and we're going to find out how much, when we use all 50 grams, how much of this do we use? And then here's how much we started with. We're just going to subtract that out. And that's how we can tell how much we actually used. Okay, so let me, I can't erase all that. Trying to go back to where I can, okay. All right, so again, what we're going to do is we're going to take this 50 grams because we determined that this is our limiting reactant. We're going to react to this to see with our AG to see how much of this is used when we use all of our limiting reactant, right? So the step when you have to find your limiting reactant, find your excess reactant, you always start with your limiting reactant. So our limiting reactant is MGBR. So we start with 50 grams of MGBR. I forget the G. And we're going to convert that to our AgNO3.
What?
Go ahead. Does anybody have any questions about how we're doing this? This part's a little tricky the first couple of times you see this. MGBR2 in 1 mole. So I'm just doing the same thing except for this time. I'm going to convert this to AgNO3. What was the molar mass of AgNO3? Does anybody remember?
$169.88.
Okay, perfect. Or right about there. So this one is 2 moles. Let's do 9. I'm just rounding, I know. AgNO3. I put that on the bottom. I'm going to fix it right now, but I don't want to forget. One mole AgNO3. See how we're kind of almost doing the same thing again, and again, right? It's very repetitious. We're, again, just following these units, mole, 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 and we get grams. And so when we do this, I do not know what we get. Put this in your calculator. If you're doing this now or later, it's great practice for your exam. I got 92.3 grams of AgNO3. Right? Okay, so what does this mean? This means when we had 50 grams of MGBR2, we used 92.3 grams of AgNO3. So what we just did is we literally just did a reaction like in a beaker, but we're just doing the reaction with math. So when we had 50 grams of MGBR2 in our beaker, we used 92.3 grams of AgNO3. That's how much it took. But we started with 100 grams of AgNO3, right? That's how much was in there, but we didn't use all 100. We only used 92.3. So if we started with 100 grams of AgNO3 and we used 92.3 grams in the reaction, yeah, we have 7.7 grams of AgNO3 left over, right? This is how much we have left sitting at the bottom. So if we had a reaction and we mixed 50 grams of MGBR2 and 100 grams of AgNO3, when our reaction was over, we would still have 7.7 grams of that AgNO3 left over just sitting there, not doing anything because it was what was left over. So how we find our excess reactant that remains? What we do, start with the limiting reactant. We started with 50 grams of MGR. Once you find your limiting reactant, you always use it. Like ignore anything else but your limiting reactant once you find it. Once we figure out that's our limiting reactant, that's what we're going to use for everything we do. Start with your limiting reactant. Convert it or react it with the excess. We want to know how much excess we used when we reacted it with our limiting reactant. So this is exactly what we did. We converted that to that, right? We just did it using math. Then that's how much we needed to use all of this. We needed that much of it. Then you look at, whoa, how much did we start with? That's how much we started with. And then you just subtract those two, and that's how much is left over. So it's really only one more piece. It's just now we did, again, almost the same thing 3 times. We're just going to different pieces, but the process of it is very similar. Okay, so any questions on this one? I have it here neater. There we are. So much prettier. So much prettier here, right? So we started with our limiting reactant. We had 50 grams of it. We converted it to our excess reactant. This is our excess reactant. We used 92.3 grams of it, but we started with 100 grams. This was our initial, was 100 grams. We used this much, that's how much was reacted, and this is how much was left over. Okay, now, just as a reminder, that excess reactant, we never used it, right? It was imaginary, and when I cross it off, you never use it again. Never be tempted to use your excess reactant for anything, right? You literally, once you do that extra calculation, you never use it. And what do I mean by that? See how I cross this off? You're really never going to use it, like ever. You're never going to use it. So sometimes people are like, oh, I'm going to use this number. No, you're not. Never, never, ever, ever going to use that extra piece. It's imaginary. It never occurred. Okay, once you find that limiting reactant, start with your limiting reactant. Okay, any questions on this? Question?